All right, good morning, everyone. So we finished up last class, somewhat working through this cruise control example. We got partially through it. So we got to if I remember correctly, we got to the idea that what we have here is we have a bunch of systems and they're all interconnected. And we're trying to understand how they behave, and we want to make sure as design engineers, we want to make sure that when we what was called close this loop, which means actually buy the hardware. Say if you work for Ford and you're in charge of some element of the cruise control, you're talking about buying hardware to close this loop where you buy a sensor, you have a computer. We'll talk about what this is later on in the class, but basically any more modern control systems are microcontrollers or full-on computers running this operation here, and you integrate that with the system you're trying to control. You need to make sure that this responds in a favorable manner. That's your job as a design engineer, right? So if you're working for Ford, you're doing cruise control, you have this nice response that your customers, being the people buying the car, like when you say set the cruise control to go from 60 to 65 miles per hour, right? You want that to go in something that's comfortable and pleasing to the people buying your car, right? So that's kind of we're really some of the goals here. Kind of getting into what we talk about the math-wise, what's happening here is that inside a computer, this operation is happening where the computer is continually checking what is your set point, 65 miles per hour, all law-abiding citizens, and say you're currently going 62 miles per hour. If you look at this element here, this is plus set point minus your measured value of your speed, right? So if you look at what is this term right here, which is what we call in this class the error, which we give a symbol E in this class. It's just basically the difference between where you want to be and where you currently are, right? And that's the metric of kind of how well are we doing, right? And so ideally, we want this term to go to 0. Right? So if we look at this, at a certain point in time, we want to be going 65 miles per hour. We're currently going 62. What this cruise control is designed to do is actually modify the input to our system, the input being the gas pedal. That's really how you control the speed of a car, right? Such that over time, your speed converges to 65 miles per hour. It may oscillate a little bit. We'll talk about how we characterize whether or not it'll oscillate later on in the class, but that's the main idea, right? Is that any questions about the main idea behind cruise control? And so you can actually, disclaimer, I do not recommend you do this, but you can actually watch this happening. I told you, do not do this, but if you do, make sure you're in a very straight section of road, which is easy to find in Columbus, Ohio, no hills. And probably some of you have seen this before, but if you set your car at 65 miles per hour, all of a sudden you start going down the hill and you look down while you're driving. Again, don't do this, but if you do, make sure no one's in front of you. You'll see that the gas pedal will depress. Actually, there's a motor moving your gas pedal for you in your car and that's doing the operation you would normally do as the human controlling the speed of the car, but you have cruise control doing that for you. There's an actually actuator doing this. And if you start going down the hill, you see the gas pedal starts coming towards you, right? Because you need basically less throttle to have your car go the same speed because gravity is assisting you when you're going down a hill. Right? So this cruise control is nice, right? Everyone probably loves cruise control. It allows you to go the same speed regardless if you're going up hills, down hills, into the wind, etc. Right? And there are many examples of control systems that we'll talk about in this class. Okay. So basically what we have here, this is just kind of the notes walking through everything I just talked about. So Y controls, some things that it helps you do. Didn't think I'd delete this section, but I did. Okay, so Y controls some elements in terms of things that this helps with. So one is it performs tasks that humans cannot do. Okay, so cruise control example, everyone here can probably regulate the speed of their car just fine, right? Humans can do this. It's tedious, but there are things that humans can't do that need to be controlled systems. So you think of lifting really heavy weights. A lot of microfabrication is below the length scale, which we can actually control. We're not that dexterous. And so there are things that we use robotics for that humans can't necessarily do. Other things that we use control for is, one is automation. And so that would be the case of cruise control. You can control the speed of your car, but oftentimes you don't want to, right? And so it's automation. So this is probably the most contentious element of automatic control. So as engineers, I'm a control systems engineer. I actually work in control systems for manufacturing. So to some people, I'm the devil in that aspect, right? Because a lot of the workforce in the United States has been replaced by robotics, right? So I'm not going to say what's right or what's wrong in that, but this is something that is definitely happening. And if I was a student in an engineering class junior year, I would want to be on the designing element of those robotics as opposed to the people who are being replaced by those robots, I guess is what I would say about that. So in terms of things we're going to talk about is actually moving robotic elements in this class, which is in manufacturing. It's in basically robots that cohabitate space with us, so robotics that are coming to being that are going to be driving around the streets, et cetera. It has things to do with automatic driving cars, autonomous vehicles, a lot of these things. And so these things they're everywhere, and they're becoming more and more everywhere. That's what I'd say about this. And so in terms of, we're going to have autonomous driving cars in Columbus soon, right, in the museum campus corridor. I forget when, but about a year from now with Smart Columbus. So these things are everywhere. If you go to the Bay Area, you see these Waymo cars driving around all the time with engineering nerds taking notes in the passenger seats. Right? These things are coming, and the elements, everything in terms of the elements of what's going on in those cars, the basic elements we're going to be covering in this class. Okay, some other examples. This one's just kind of fun. We're not going to talk about anything this complicated in this class. But this is just a really cool example. This is a lab out of Zurich, Switzerland. And they do some kind of crazy stuff. Not really too important for anything, but it's fun to watch. So it's good to give an introduction lecture. But what they have here, I'll pause this in a second. All right, so what's going on here? Let me reverse that just one bit. Okay, so they have a quad rotor, or a drone, right? So here are your 4 rotors, and on the top they have a tennis racket. And what they're going to do is they're going to turn this into a robot that can basically keep a ball juggling in the air. So they have a few things. You can see these little reflective balls. These are the same things that are used in video game development when they're looking at features on people, and they're trying to represent that in terms of video games. Here they're looking at the position, angle, orientation of this quad rotor. All right, so it's going to fly up in the air. And they can also pick off where's the ball with a bunch of machine vision systems in the air. So this robot can juggle with another robot. Oh, every so often it makes a mistake. It can juggle with itself. Oh, never mind, that wasn't it. This is juggling with another robot. I forget what was actually in this paper, but I know they do some machine learning. It can juggle with itself here. It makes some mistakes. This video is a few years old. Maybe it's a little better now. I think it's the end of the video. Okay. Anyhow, so there's just some really cool stuff. We're not going to go into anything this complicated in this class. What's underlying that is quite complex. But the basics of what's going on there in terms of understanding how do you track a moving object, right? That's what we'll call a reference signal in this class. How do you make sure this happens in a stable manner? We'll talk about stability extensively in this class, many weeks of discussing stability, other performance metrics, et cetera. The basics of this will be in this class. Other things that are control systems you may not necessarily think of. This is an example of homeostasis. This is how our bodies regulate temperature. And so this is not something that any engineer has designed, but this is something that engineers have analyzed this type of system in the framework of control systems. So just take, for instance, this temperature regulation issue where your body gets too hot. So, wait, what am I looking at here? Let me remind myself what's going on here. Okay, so sorry, that was right. So your body gets too hot. So basically, what you have here is too high. Oh, never mind. Sorry, this is your body's too cold. Okay, never mind. All right, let's walk through this again. All right, so two conditions, right? So you have the ability to sense temperature in the body, right? And so you're always trying to regulate to 98.6 degrees, right? That's the average for a healthy adult. And so your body has the ability to sense what is the temperature. Your certain area of your brain, the hypothalamus, will then activate. If your body is too cold, it'll actually dilate your blood vessels to cause more blood to flow through, increasing your body temperature. And if your body is too hot, it'll actually activate sweat glands to activate or increase evaporative cooling. Right? So these are elements that are built into yourself that help you auto-regulate temperature in your body. So just like in the cruise control example, if you're going too slow, the car will then automatically depress the accelerator pedal more to give more gas to the engine. Same thing here, if your body temperature is too low, you can dilate your blood vessels to increase blood flow and then increase your temperature. Right? So this is just another example of that. Yes? So would that be considered a feedback loop? These are all, yeah, we haven't introduced those terms yet, but these are all feedback loops. Yep, so feedback control would be usually the full term for that. So that's a feedback loop. Going back up, you'll see this directly here. If you look at this block diagram that we had for cruise control, oops. Okay, so, all right, so this element, if this didn't exist, that wouldn't be feedback, but it does in cruise control, right? So we have our current speed of our system via the sensor feeding back into our system, right? So this whole idea, I talked on Monday about the outputs of a system also influencing the inputs of the system, right? So you have the output of a system is the speed, it goes into our engine control unit, and then it goes in and then actually is processed, and it becomes now the input to our system. So it's a feedback loop. Yeah. So in your freshman engineering, did anyone see PID control? A few heads are nodding. All right, we talk about PID, proportional integral derivative control in this class. Yes?
So do you ever measure, like, not just the state of the air, but the derivative of the air, or higher order terms?
Yeah, so proportional, state of the air, derivative control and PID controls the derivative of the air, integral is the integral of the air. Yeah, we'll talk about that ad nauseum in this class. Yeah. Okay. All right, so that's the introduction to this class. So that was more the fun part of today's lecture. Let's talk about complex variables, because that's what everyone wanted to hear about today. Okay, so complex variables. So in this class, kind of a general outline of what we'll be going through here. Just complex variables, functions of complex variables. You'll recognize these as transfer functions or Laplace transforms that you would have seen in 3260. And also we'll look at some trig with complex variables. So everyone should have seen complex variables in your math classes at Ohio State or elsewhere. You should have also seen them a little bit in 3260. I think it's not a stretch to say that this class will use complex variables more so than any other class you've seen at Ohio State or will see in your bachelor's degree. Okay. So this first lecture is just to give you a refresher. I guess second lecture is to give you a refresher on complex variables and also look at some graphical methods that we'll be using in this class that you may or may not have seen. If you haven't seen them, if you have seen them, you probably haven't used them that much. So we're going to go through some examples with the graphical forms of complex variables. And if you look at homework 1, there are, I guess, 2 homework problems that are looking at complex variables. Kind of, hopefully it'll be a refresher. There may be some new stuff in there. So complex variables. So first off is some terminology. So we are going to use the variable s for a complex variable in this class. We're going to say x is in the set of this, x is in the space of complex variables. So if we see this symbol here, so that's not drawn very well. So we say this is a variable s is in the space of complex variables. Okay, so the question is, what do we mean by that? So what we mean by that what's going on here? This is supposed to be blank. There we go. Open up the wrong one. Sorry about that. Okay, I'll just really quickly copy this. Okay, back on track. All right, so a variable s is in the space of complex variables. What we mean by that is that s can be composed of its real part and imaginary part, right? So unlike a number, say 5, which only has a real part, s has a real part and an imaginary part. So we would say that s is composed of its real part. Oftentimes in this class we give this by sigma, and its imaginary part. So I here is the square root of -1, the imaginary number. And so then omega is the imaginary part of this complex number. So some properties as you should remember. So if we have I squared, that is equal to -1. And we would say that I is a complex number, so we'd write it this way, right? But I squared is because it's -1. That's on the negative real axis. That's a real number. Okay, omega is a real number. Sorry, sigma is a real number, and omega is a real number as well. Okay, so graphically what this looks like is that if we have some sort of variable s, we can always plot this in the complex plane. Okay, so if we have some sort of variable s, it's right here, we would say that this is composed of its real part, sigma, and its imaginary part, omega. Okay, that hopefully is a review for everyone. All right. The next thing to introduce is an Euler's equation. And this is going to be we're going to start talking about the complex form, or sorry, the polar form of complex variables. Okay, so Euler's equation. All right, so Euler's equation deals with the exponential. So if you have e raised to the I theta, we can also rewrite this as, so this would be in polar form, we could also write this in Cartesian coordinates. So e to the I theta is equal to cosine theta plus I sine theta. So what this means, this describes complex variables along the unit disk. Okay, so if I draw the unit disk here, as accurate as I can draw a circle. Okay, so this is 1, 1, negative 1, negative 1. Okay, so if I draw the unit disk, I can describe any complex number along this unit disk as basically by theta. I have basically the radius of this vector as value 1, and then this angle as theta. Right? So looking back at this, if I want to say where is this point in the complex plane, it is equal to 1 cosine theta on the real axis times 1 sine theta in the imaginary axis. Right? I want to talk about this number in the complex plane. Right. Has anyone not seen this before? Okay, good. All right, so then translating between the Cartesian coordinate form and polar form, this allows us to do this, is we say that we have some sort of complex number. S is equal to sigma I omega. I can rewrite this as its basically vector length or array length or magnitude e to the I theta. Okay, so what I'm doing is I'm scaling this Euler's equation by r, by uppercase r. Okay, so what this means is if alternatively I want to look at this equation, if I had S is composed of omega and sigma in the imaginary and real direction respectively, I can rewrite this as a vector with length r and angle theta. So keep in mind that theta in this class, and pretty much any class you'll take, theta is always referenced to the positive real axis. Right, that's just the convention that people have set. Okay, so if I want to know what R is and what theta is, then we look at trigonometry to figure that out, right? So filling this in, S is equal to sigma plus I omega. R in this case, just using Pythagorean's theorem, sigma squared plus omega squared. Theta is equal to inverse tan omega over sigma. Okay. Any questions about that? So one of my goals, at least for this lecture and for the early parts of this class too, is to break you all of using Cartesian coordinates for complex numbers. So I think probably the first exposure you had to complex numbers was Cartesian coordinates. So that probably seems more natural, but the most easy framework in this class for solving problems is going to be actually in polar coordinates. All right. So just a reminder, this is the Cartesian coordinate form. This is the polar coordinate form. This is cart. This is polar coordinate form. Okay, so if you ever get to a problem, especially let's say homework 1, problem 1, where it seems really difficult to do it in Cartesian coordinates, think about how you could possibly express this problem in polar coordinates, and I think 9 times out of 10 it's going to be much easier to do in polar coordinates. All right, so just a hint for homework 1 and pretty much the rest of this class. So I'll do an example on that, but basically, polar coordinates are going to be your friend. If you haven't really seen graphical forms of complex numbers and how to use polar coordinates, this lecture will help, and I hope you can go back to your notes from calculus or algebra or whatever when you saw this last and go through that as well as a refresher. But this first example is kind of just going to show. I'm not going to go through the polar or the Cartesian coordinate form of this. I'll go through the polar form of this. Okay. So very first question here is our example, is example 2.1, is evaluate f of s, and this may look a lot like a transfer function. This is no accident, but it's just looking at ways to evaluate transfer functions, or we're going to be doing a lot in this class. Okay, so evaluate f of s at s is equal to 1 plus I is the problem statement here, right? So anytime we see evaluate a function, right, it just means evaluate a function at a certain value of the argument. That means just plug in the argument into the function, right? And so the notes would go through and shows how you would do this. Basically, everywhere you see an s, you put in 1 plus I. You work this around a little bit. You do complex conjugate multiplication of the top and bottom to simplify this, and you get this in this expression here, which doesn't really matter too much, but I'm going to show you how you can do this in polar coordinates as well. So this would be just evaluating a function at the given argument is a complex variable. All right. So the alternative form of this is let's look at a polar coordinate solution. So same exact problem. This is still example 2.1. But now let's just look at a little side problem here first, then we'll build from here. So say, for instance, we have two variables, S1 and S2, and these are in the complex plane. Okay, so we have S2 right here, and we have S1. So these are just two different numbers. They're both complex. And what we want to know is, what is S2 minus S1? Okay? So in Cartesian coordinates, if we wanted to go that route, we could say, okay, this S2, this has a real value of sigma 2, as imaginary value of omega 2. And likewise, we can write the same thing for S1. And we can say that S2 minus S1 is equal to sigma 2 minus sigma 1 plus omega 2 minus omega 1 times I. Right? So that'd be one way to do this. If we want to use polar coordinates, we're looking at a different framework, which we can actually have very graphical methods to do this. Instead, we can look at, we're applying this in two-dimensional space. We can write this as in vector form, right? So we can say this is a vector with a tail at S1 and a head at S2. And so we can now describe the subtraction by the magnitude of that vector and the phase angle of that vector to do the subtraction. And so then I would say that S2 minus S1 is equal to R e to the I theta. Any questions on that? All right, so let's actually get to our problem and we'll show how you can use this for a problem here. Okay, so getting back to the problem at hand, if I want to know what is f of s this is just copying the problem as stated. F of s is equal to s plus 5, s plus plus 1 plus I, s plus 1 minus I, and evaluate at s is equal to 1 plus I, we can pose this problem in pretty much the same exact form as we just saw, graphical form. And what we're doing is we're going to do a kind of a change of variables here. Okay, so instead of saying s plus 5 in the numerator, I can just do not change of variable, that's the wrong word, just a mathematical trick. So if I can say s plus 5, I can rewrite this, if I wanted to, as s minus negative 5, right? That's equivalent. I haven't changed anything there. And I can rewrite the denominator s minus negative 1 minus I, and s minus negative 1 plus I. Right? So I haven't changed anything. I've just flipped around some negative signs. Right? So now this is starting to look like what we had before. Okay, so s is a complex variable, right? It's 1 plus I. Right? Negative 5 is a real number, but it still can be plotted on the complex plane, right? It's on the negative real axis. So I can come up with a completely graphical form of this expression. So I can look at this equation and figure out what this is based purely on geometry. Okay, so we're evaluating at s is equal to 1 plus I. All right, so if I look on the complex plane, where is this? Here is, I'll just make a coordinate system here. S is right here, right? 1 plus I. Okay, and then I can look at the other components of this. I have s minus negative 5. So negative 5 is way over here. It's going to be a little bit out of scale. All right, my other complex variable is negative 1 minus I. That's right here. And my other one is negative 1 plus I. Here. Okay, any question about what I did there? Yes?
Why don't you bring it into the negative form? So you have like s minus on the top.
Yeah. Give me one moment. I think it'll become clear. Okay. So before we were looking at, this example just above was S2 minus S1, right? And we looked at a graphical solution to this, right? So we're looking at one complex variable minus another complex variable, right? So by putting it, let's say for instance, turning s plus 5 into s minus negative 5, I'm making it in the form of one complex variable minus another complex variable. Okay, so how we look at this from a graphical point of view is I look at and say, all right, if I want to understand what is s minus negative 5, well, that's simply this vector going from negative 5 to s. So I can call this R1. This would be theta 1. S minus negative 1 minus I is this vector. I can call this theta 2. And then the last one is S minus negative 1 plus I, which is R3. Theta 3 is not too easy for me to draw because the angle is 0, right? So that would be the last angle. Okay, so now if I want to know what is this function evaluated at the complex number, 1 plus I, that's going to be equal to R1 e to the I theta 1 over R2 e to the I theta 2, R3 e to the I theta 3. Okay, then simplifying this, I want to turn this into a single complex number. or sorry, more simple form in polar coordinates would be R1 over R2, R3, e to the I. You have to remember how exponents work in terms of when they're in the numerator and denominator. It's going to be theta 1 minus theta 2 minus theta 3. All right, so then R1, right? R1 has a real part of 6 and an imaginary part of 1, right? So if I look at what R1 is, be square root 6 squared plus 1 squared. R2, this has a real part of 2, right, and an imaginary part of 2. All right, last term. All right, real part of 2, imaginary part of 0. E to the I. Now we have to look at all of our angles, right? So same thing with theta 1, real part of 6, imaginary part of 1. So this is inverse tan of 1/6 minus inverse tan of 2 over 2, which is 45 degrees. The last one is 0, because that's going due east, straight all the way to the right. In the phase angle. Okay. Any questions on that? Okay. So this boils down to, if you then plug this into your calculator, the whole point is you get exactly the same answer as what we saw if you were to evaluate this using Cartesian coordinates. It's just a different way of getting it. So if you plug this in your calculator, you should get this number here. All right, it's more graphical. We'll be using this a lot, especially for design of controlled systems. So we're looking at behavior in the complex plane. Yes?
One of the terms doesn't have an S minus something.
So you were asking if it doesn't have an S minus, you mean, for instance, if you had just like, instead of this numerator being, this was S plus 5, like same denominator, but you said the numerator has this, right?
Like, if the numerator is a constant, or the denominator is like just a constant.
Oh, okay. So this would be like 5, right? Right, instead? Yeah. So this is, you would, in terms of looking at this from complex numbers, this is 5 times anything. So if we look at, if I wanted to write f of 1 plus I can write this as, say, we have this as R1 over R2, R3, e to the I, and then whatever this was, right? This 5 would just pop out because it's a product on the magnitude. Does that make sense? Okay, so some trig with complex variables. So just a reminder, we just went through this. This is Euler's equation. What this does, it allows us to put terms like sines and cosines in different forms. So for instance, if I want to know, if you're given the question, maybe this is more looking at identity. Let's look at just the case of 1/2 e to the I theta plus e to the negative I theta. Okay, I think you'll see in a second why I'm writing this, but just say that you were given this, and now try and write this as a real number. All right. So given the Euler's equation, we can rewrite this as 1/2 e to the I theta is cosine theta plus I sine theta. E to the negative I theta is going to be cosine negative theta plus I sine negative theta. Okay, so some trig identities. Cosine negative theta is just equal to cosine theta. Cosine or sine negative theta is just equal to negative sine theta. Okay, so we now look at these terms. We have cosine theta, everything's multiplied by 1/2 up front. So that gives us 2 cosine theta times 1/2 is just cosine theta. I sine theta minus I sine theta is equal to 0. All right. So this is the polar coordinate or Euler form of cosine some number. Yes?
Could you not just take the negative and put it with the I in front of
So what is the?
you took the negative to be with the theta. Could you not just take it to the I?
Yeah, that could have worked. Yeah, that would work. In your notes, this is then the same thing worked out for sine here. Okay, and so just to conclude, this is the Euler form of these really common complex functions that you use. So we have 1/2 e to the I theta plus e to the negative I theta is equal to cosine theta. And then we have 1/2I e to the I theta minus negative I theta is equal to sine. Any questions on that? Okay, so last example from this lecture before we go on to lecture 3 is the problem says rewrite. We have some sort of function x of t. You would have seen this often in 3260 where you see, say, x of t is equal to a cosine and sine added together. They each have different magnitudes of those cosine and sine functions. So we have exactly the same thing here. X of t is equal to c1 cosine omega t plus c2 sine omega t. And we want to write this in the form of a single cosine function with a magnitude and also a phase shift associated with it. So you probably saw this a lot. We're going to be using this form more in this class than this form, or you probably saw this form more often in 3260, right? Just sums of sines and cosines. Right. So we're just going to go through some manipulations here and basically be trying to come up with, via polar form of complex coordinates, how we express this function in terms of, in this way. Okay. All right, so doing a substitution using the polar form of harmonic functions, we have x of t is going to be equal to c1 over 2 e to the I omega t plus e to the negative I omega t plus c2 over 2I e to the I omega t minus e to the negative I omega t. Right, so that's just substituting in that form, in Euler form for trigonometric functions. And we're going to try and manipulate this and move this around to try and understand how to write this in a different form. Okay, so first thing we can see is we have, in terms of just adding these together, the factor that's preventing us from doing that is we have an I in the denominator here. All right, so we want to understand how do we handle an I in the denominator. If you're using Cartesian coordinates, you probably just multiply top and bottom by I, right? That'd be your standard method. But polar coordinates, we have to look at what does I in the denominator represent. Okay. So if we look at an I in the denominator, one over I. If I want, I can rewrite this as, let's just do it this way. If I look at what is I on the complex plane, We're just looking at I. We're looking at this portion right here. I in the complex plane is along the imaginary axis, and it's up 1 unit along the imaginary axis, right? So if I want to say, this is I right here. Okay, so usually in Cartesian coordinates, we would just write this as I. In polar coordinates, we would write this. This has a magnitude of 1. So I would be equal to 1 e to the I, and then its phase angle, right? So its phase angle here is 90 degrees, right? If I reference phase angle from the positive real axis, this is 90 degrees, or pi over 2. Okay, so if I want to know then what is 1 over I, 1 over I is then equal to 1 over 1 e to the I pi over 2, which is equal to 1 e to the negative I pi over 2. Okay, this is in the denominator. Okay, so the short answer here is if you divide by I, you're instituting a phase shift in your complex function of 90 degrees, negative 90 degrees. Right? I think you can probably see that the converse is true. If I were to multiply the function by I, I'm instituting or applying a phase shift of positive 90 degrees, or positive pi over 2. Right? Think about that statement when you're doing homework problem 1. Okay, so what we're doing here is if we look at what is sine as opposed to cosine, sine is essentially, it's a little bit more complicated, but part of it has to do with a phase shift of negative 90 degrees. It also has a negative sign here. It's a little bit more complicated than what I just said, but part of it is you have a division by I, that's a phase shift of 90 degrees associated. Okay, so taking this form of x of t, let's now rewrite it with this new information that we have now. So this is going to be nothing changing with the first term here, c1 over 2, e to the I omega t, plus e to the negative I omega t. So nothing changed there. On the second term, we do have things changing. We can write this as c2 over 2, e to the I omega t minus pi over 2, minus e to the negative I omega t plus pi over 2. So I got rid of the I in the denominator. I'm not quite there yet. Still going to need a little bit more work here. So rewriting this again, I'm just going to group terms here in terms of everything that's e to the I omega t and everything together, and everything is e to the negative I omega t together as well. Okay, so all terms e to the I omega t. So we had a c1 over 2, c2 over 2, e to the negative I pi over 2, plus e to the negative I omega t, and essentially the same form, but a negative sign instead. Okay, so you see these are pretty much the same form. We'll talk about the differences here in a second. But what we have here is we have we have a real number, we have a complex number. We'll try to understand what is the equivalent complex number for these two. So let's just take this first example right here. We have first term c1 over 2. All right, second term is c2 over 2 e to the negative I over 2, right, which is along the negative imaginary axis. This is at c2 over 2. So the equivalent complex number here has this radius and this phase angle. And so that means I can write then this first term try to keep this all on the same page. As its magnitude, right? So its magnitude is going to be just Pythagorean's theorem here. It's going to be equal to 1/2 square root C1 squared plus C2 squared e to the I omega t e to the negative I inverse tangent of C2 over C1, right? C2, imaginary part over real part, right? Second term is going to look very, very similar, except we have a negative sign instead. So this imaginary part will actually be along the positive imaginary axis. And we're going to have 1/2 square root of C1 squared plus C2 squared e to the negative I omega t e to the I tangent C2 over C1. Okay, so in the last few minutes, I just wanted to finish this up. What this is boiling down to is getting into the form of cosine, right? So before we said that cosine, if we want to express something cosine, it's going to be some sort of constant. Sometimes it's sort of constant out front, e to the I omega t plus e to the I negative omega t. So that's what we have here. So our constant out front is going to be equal to 1/2, grouping these terms, C1 squared plus C2 squared. Our exponential terms here are going to be e to the I omega t minus inverse tan C2 C1 plus e to the negative I omega t minus inverse tan C2 over C1. All right, so now this is in the form of cosine. Yes? Yes, thanks. Yes. All right. Where am I missing it? Second term. Sorry. To the right? Oh, thanks. There you go. Thanks. All right. Now, the kicker, this is in the form of cosine, right? So I can now write this as square root C1 squared plus C2 squared cosine omega t minus inverse tan C2 over C1. Okay. So you may have seen these in trig identity tables, etc. Before, you probably use this in 3260 when you're looking at Bodie plots, frequency responses, etc. But this is the main thing. I look at these notes for kind of some of the manipulations because that's going to be important in terms of what happens when you multiply by I, divide by I, etc. In terms of this identity, you can just memorize it or write it down somewhere. That's going to be very, very helpful. But this is just kind of some of the manipulations you would go through to get to this. Yes? All right. I need like some sort of macro that does that for me automatically. All right. Thanks. When I was writing it, I was like, don't forget it. And then mine's getting old and people. Yeah. Yes?
How'd you know C1 over 2 is in a real axis and C2 over 2 is in the imaginary?
Okay, so that's going back a step here. So that's right here. So if you look at C1 over 2, there's no imaginary term in front of it, so that's a real number. This one is C2 over 2, but then it has a phase angle of negative 90 degrees. So it's along the negative imaginary axis. All right, with that, I think we're out of time. We'll get into review of 3260, a pretty quick review, but it'll try and highlight the most important elements. Sorry?